Okay, so first of all, thank you to the organizer for this nice opportunity to present in this nice venue. And so today I would like to talk about identification and state estimation in the context of the Kuman operator in analytic function spaces. And so we'll consider the Kuman operator and also its adjoint in space of analytic functions. And why do we do this? But first, I think it's because we know that there are nice spectral properties in these spaces, but also basis of monomials is orthogonal. And we usually use monomials in numerical approximation. So it's nice to have an orthonormal basis. And also we have this reproducing property that, for instance, Carl already mentioned, and we'll see that it is very useful for our application. And so, as I said, we'll, in a first part, consider identification. So typically, a data-driven approximation of the operator that we'll call analytic EDMD. And in the second part, we'll consider state estimation. Okay, so before plunging into the result, I would like just to briefly explain again for those who are not familiar with this concept, the concept of reproducing kernel Hilbert space. So these are Hilbert space, so space of function with an inner product. And in this space, evaluation functional, so a functional that to each function will give the value of the function to some at some point x is bounded. And a consequence of this from a Riesz representation theorem is that this evaluation functional at x can be represented by what we call the reproducing function kx, which is such that if we take the inner product between kx and f, we get the value of f at x. So this is the function in the RKHS, which represents our evaluation functional. Because of this, we can consider the inner product between two reproducing functions, kx and ky, and this scalar value is given by the value of the kernel evaluated at x and y. And here we'll focus, as I already mentioned, on analytic spaces, so space of analytic functions. And the prototypical spaces of analytic function is the Hardy space. So we'll really focus on the Hardy space, although we could extend the set of spaces that we could consider like the Fock space as Igor did. But here we'll focus on the Hardy space. So the kernel is this one. I don't know how to pronounce this, so I will not pronounce it, but Xeg, okay. So this is the kernel. In this case, monomials are not only orthogonal, but also orthonormal. So this is really the nice property that we get. The norm or the square of the norm of the function is simply the sum of the square of the Taylor coefficients of the function. Okay, so regarding the setting notation, I will briefly mention that we consider continuous time dynamics, x dot is equal to f of x, so autonomous system in this case. We'll denote the flow generated by the system by phi t, and we'll focus on dynamics that possess an hyperbolic equilibrium, and in some cases, even we need a stable equilibrium. And we'll also assume that the vector field is analytic, which makes sense since we consider spaces of analytic functions. So in particular, the vector field F is in the Hardy space in this case, in the RKHS. Okay, regarding the Koopman operator, since it's in continuous time, we have a Koopman semigroup that I denote by K. So it's the composition with the flow of any observable in the RKHS. And we'll consider what I call here the Lie generator, which is the usual infinitesimal generator, which is simply given by the Lie derivative associated with the vector field. I prefer to call it Lie generator because we might not be able to define this limit because we might not have the strong continuity property. So I prefer to stick to this definition and call it the Lie generator, but this is just a detail. Okay, so far so good. So now I would suggest we start with the first part, so identification with analytic EDMD. This is a joint work with Igor. And the first idea is that in this RKHS, so the RD space, we could represent the operator in the basis of monomials. So in some sense, we have a separable space which is isometric to a small L2, so the space of square summable sequences. And the sequence corresponds to the Taylor coefficient simply. So the components in the orthonormal basis of monomials. And so we can represent our Kuhlmann operator as an infinite matrix given by all these inner products. And something that we know for years is that this operator has a nice block triangular structure, which is reminiscent of the Scrooge form that Zlatko and Igor studied. And we also know that if we truncate this matrix, then we keep this block triangular form. And this is really nice because we keep the spectral properties in the sense that if we truncate the matrix, we compute the eigenvalues of this matrix, we still get the same eigenvalues as this infinite dimensional matrix. And so in some sense, we have no spurious eigenvalues. But to do so, we have to truncate. And this truncation is what I call the Taylor projection. It's just that we cut the Taylor expansion at some order. And so it's an expansion, a projection on a basis of monomials to some order that we can simply rewrite like this because it's an orthogonal projection in our specific case. And as I said, this projection will satisfy this property, which means that it preserves the block, the triangular block structure. But the question is, how can we compute this projection from the data? So we want to use this new projection to depart from the usual L2 projection that is used in EDMD and do this from the data. And so we'll do this as follows. So for each columns of our Kuhlmann matrix, we need to compute the projection, this Taylor projection, applied to the Kuhlmann semigroup, applied to some EJ, which is, I forgot to tell, this is the basis of monomial, so I call it EJ. And so we have to compute this sum. And in particular, we have to compute this inner product in the RKHS, so in the RD space. And the trick here is that computing the inner product between two functions is difficult. We have to know, for instance, the Taylor coefficient, but from the data, we don't know them, so it's not possible. But because it's an RKHS, what we know is the inner product between this reproducing function, kx, ky, this is given by the kernel. And so what we do is, in fact, we'll project our two functions, kt, ej, and ei, onto a subspace of reproducing function, and then we can compute the inner product. So I skip the detail, but it boils down to computing this product where you consider the value of the monomial at some data points here, the value of kt, ej at some data points, so ej, y, where y are the data points that are mapped by the flow. So I have x1, y1, x2, y2, and so on, as usual. I have these two columns, and in between, I have the inverse of the kernel matrix computed with this kernel, Zeiger kernel. And so if we simplify the notation, we recover here the columns of x, here the columns of j, and in the end, this here is just kij. So the matrix K that we want here is simply given by this simple expression. We can add some regularization if we want. So this is our analytic EDMD, which is kind of Taylor projection of the Kuhlmann operator on a subspace of monomials. And we expect that this captures the spectral properties in the analytic space of function. And so we tried van der Pol dynamics with a stable equilibrium. And you can see that what we get are the red crosses. We can really capture the well-known lattice of eigenvalues, where these two ones are the eigenvalues of the Jacobian matrix at the equilibrium. We can compute the Taylor expansion of the eigenfunction here in absolute value. We also did another experiment among many. We sampled data points, but far from the equilibrium. These are the blue dots, which are mapped to the red dots, so we are always far from equilibrium. And with these points, we can still capture here in red exactly, or almost exactly, the eigenvalue at the Jacobian matrix at the equilibrium, which is explained simply because we exploit the analytic properties of the eigenfunctions and of any function. And so even though we only know the functions here, we know them everywhere because they are analytic. And you can see that EDMD, for instance, or ODMD cannot capture properly this eigenfunction, which is known. I added this result also because here we compute with different data points, and we can see that the error here in blue decreases as expected. We can also compute some bounds on the error, but I will not enter into the details. Okay, so I think that's it for analytic EDMD. Now I would like to talk about state estimation, which is a joint work with a student, Judicaël Mauroy, and my colleague, Joseph Winquin from University of Namur. And here the idea is that we have a nonlinear dynamics and some output, and from the knowledge of this dynamics and the output, we would like to recover the state. And the idea is that instead of doing this in the nonlinear dynamics, we'll do it in the linear Koopman system. So we can rewrite here f dot, where f is our observable. So it's an abstract differential equation, infinite dimensional one. And we can rewrite the output like this, and we can check that with this operator Cx0, which is just taking the inner product with our with the reproducing function at x0, y will be the y, I mean the output that we expect. So we can recover the system like this. But there is an issue. The issue is that the initial condition here should be the output map H, which is known, while the output map here, it's given by this Cx0, is unknown, which is not the usual setting for state estimation, because for state estimation, we do not know the initial condition in particular. And so the trick here is to consider the dual framework with the adjoint generator here. And now the output is given by this output operator CH, which is the inner product between f and h. And the initial condition will be the evaluation functional or the reproducing function at x0. And now this is, I think, no, I did not put it. So this is unknown and this is known. So this is the right framework. Again, if we do the computation, we can check that y correspond to what we would expect, so the true output, where here we have the solution of this abstract equation. So this is just the adjoint of the Koopman semigroup. And we have this nice well-known property that this is the reproducing function at phi t of x0, so along the trajectory. Okay, so the idea is that instead of estimating the state of the nonlinear system, what we'll do is to try to estimate the evaluation functional for the dual Koopman system. So this is really a take-home message for this part about state estimation. And to do so, we'll just design a Lüneberger observer in infinite dimension for this Koopman dual system. So we'll add a dynamics for the estimation for our observer, which is just mimicking the dual Koopman system, but we add this term where we have here L, which is an injection operator, and here we just take the difference between the true output and the output that we would obtain with our guess, which is F hat. So the the observable that we try to guess. And the initial guess will be simply a reproducing function at some guessed initial condition x0 at. And we can show that under some technical condition that I don't want to focus here, we can have the following result. And here the idea is to observe the slower modes. So we'll consider modes that are slower than some decay beta, and we'll observe those modes. And the other one, we know that they will decrease very fast, so we don't observe them. And so the main condition is a kind of observability or detectability condition on these modes that we want to observe, which just tell us that the eigenfunction associated to these slow modes should not be orthogonal to the output map. So this is related to a known observability condition in the Koopman framework. And in this case, we can show that our solution here will converge to the true solution of the dual Koopman system. But it converges weakly, which means that we have this kind of convergence for each function g, and it converges at a speed which is larger than beta. So, and we can make this decay rate as fast as we can, at least in theory. Okay, regarding implementation, so in practice, because we have this conversion for any g, we can consider a monomial of degree 1, for instance, g of x equal to xj. And this means that the inner product between our estimate and xj will converge very fast, arbitrarily fast, let's say, to the jth component of the state, because if we take the inner product between this and this g, which is xj, then we get the j component of the trajectory. And we apply this to the Lorentz system with a stable equilibrium. And we can show that we converge faster than, for instance, a linear observer based on the linear dynamics, the linearized dynamics. This method is actually very similar to the method designed by Amit Surana almost 10 years ago. The difference here is that we observe the slower mode, so we can make it as fast as we want. And we also provide a theoretical framework, at least for the case of equilibria. Okay, so it's almost the end of my talk. I would just like to present an extension to this framework, which is about a probabilistic extension. So just to summarize, the idea is that we have an initial condition, a true one, which is the reproducing function at x0. And we have a deterministic guess, which is somehow the reproducing function at some x0 at that we guess. And as we've seen in the RKHS, we have these three conversions between our estimated observable to the true solution, which is the reproducing function along the trajectory. If we go to the basis of monomials, so in small L2, it means that the components, which are just the inner product between our solution or our guess and all the monomials, will tend to the true one, and the true one is this one, inner product with the monomial, which means that it's just the monomial evaluated along the trajectory, which is typically what we call the lifted state. And so our guess in the monomial basis will converge to the lifted state somehow. But we could go further. We could say, oh, I can do this initial guess, but I could also have another guess. I have no limitation about this. I could consider a kind of probabilistic guess in some kind of Bayesian context, where I would consider this k rho 0 at, which would be the reproducing function, the representer, let's say, of a functional associated with some distribution rho 0 at. Meaning that if I take the inner product between this guy and f, I consider this integral weighted by my guessed distribution. And so I can consider this as an initial guess, and somehow it's like considering a prior distribution for the initial state. Again, we can have the same result, that we have a weak convergence. This is not proven yet, but I'm pretty sure. So the students still work on the theory, but I'm quite confident. But it's not proven yet, but it should converge to the true value. And what we get in the basis of monomers, we get the inner product between, let's say that after some time t, our guess is k rho t, so it's the representing function for some density distribution rho t at. Then the state that we get, or the component in the monomers, would simply be the inner product between this k rho t at and all the monomers, which means that we'll get this integral, which is nothing but the moments of the density, which means that we can also recover the density solving the problem of moments. And so it's a kind of extended probabilistic approach compared to the initial deterministic approach. And so just as an illustration, if we take the initial condition 0.5, with our previous method, we have a guess here at 0.3, we get this convergence. The real state is in blue here. But now, if instead we consider a uniform distribution, we see that convergence is already better. And if we consider a beta distribution with the same mean as the deterministic guess, again, we converge faster. I also put a movie, although I'm not sure it's completely accurate at this point, but just for an illustration, we start from a beta distribution, and we see that we converge to something that should be in the end a Dirac function, but the simulation does not give a Dirac function, but solving the moment problem for a Dirac function might be a bit difficult. So I expect some inaccuracy in the end, but just to show you that we can have an initial density, a prior density, and then compute a posterior density for our state estimation. Okay, so I think it's time to conclude. So there are a few perspectives. For analytic in DMD, we could apply it to some application like stability prediction. A big issue is to extend the framework to limit cycles and still keep this nice triangular form. For state estimation, the probabilistic approach is still an ongoing work. We could apply this to the data analysis. And we could also extend the theory at least to more general dynamics. So with this, I thank you for your attention.